Hello and welcome to this lecture number 3 of the course Robot Motion Planning. In the last lecture number 2, we looked at degrees of freedom and the various joints that are there. So today we'll very briefly revise what we are doing in the last class, and then we'll move on to the next topic, that is, after you assemble the various joints and make a robot, then what is the work volume or the area inside which the robot can move its gripper. Okay, and then we'll move on to transformations, that is, a robot essentially moves in space. So we need to know the relation between one joint and the other joint with respect to the base. Okay, so we'll first start off with revision of the last class, then we'll talk about work volume, the shape of the work volume when you make robots using different kind of joints, and then we'll talk about the basic transformations, that is the rotation transformation, and then we'll move on to homogeneous transformations. Okay, so we are talking about work volume and then transformation. So very quickly revising about what we did in the last class, we said that a robot is made up of links. So these are the links, and the links are connected by joints. Okay, and at the end we have the end effector or gripper. And the base of the robot is fixed. In this case, we say that the base is fixed; it doesn't move. Okay, so this is a fixed base robot. Okay. So these are the different parts of the robot, and we looked at the various joints or the various types of joints which are possible. We saw that we have a prismatic joint, in which case we have the variable, which is the variable distance, which is x, and it has 1 degree of freedom, and the variable is the distance x. Okay. Now this is a revolute joint, the one on the left side, and in the revolute joint we saw that this has a rotating degree of freedom, which is theta, and there is a stopper there, so it cannot move up and down. Okay, so there is a stopper there, and it also has 1 degree of freedom, and the variable is theta. It also has 1 degree of freedom. The other kind of joint is a cylindrical joint, and the cylindrical joint has 2 degrees of freedom. In this case, there is no stopper, so there is no stopper here, so it can move up and down, and this is up and down x, and there is a variable theta. Okay, so this has 2 degrees of freedom, and the variable is theta and is the translation distance x. Okay, so this is what we can call a prismatic joint. It is also called a translational joint, that the variable distance is a translation, and it is represented as a P. It's also called a P joint. This is called an R joint. This is called a C joint, a cylindrical joint. And then we also have a spherical joint, which has 3 degrees of freedom, which means that it can move about the 3 axes. If this is my x, y, and z axis, then it can move, it can rotate about the 3 axes, and we have 3 degrees of freedom. So that we can call it alpha, beta, and gamma. Okay. Now we also saw that most robots are made up of the revolute joints, and 99% robots are made of revolute joint. But when you want to do assembly application, where you're assembling 2 parts, and you need a straight line motion, then we normally use a prismatic joint. So prismatic joint is basically used for straight line motion. So straight line motion. Okay. The minimum parameters required to specify the configuration of a system is called the degrees of freedom, and we said that for a freely floating object in space. Okay, so freely floating object. Okay, we have this freely floating object. This can, if we assign an axis there, let's say I'm going to assign an axis, some other color. This is my x-axis, that's my y-axis, and that's my z-axis, x, y, and z. Then it has 3 translations in the x direction, y direction, z direction, and it has 3 rotations about the x, y, and the z. So this one has 6 degrees of freedom. Okay, 3 translations and 3 rotations. Now, when we talk about a robot is fixed at the base, like the one we just saw. So this is fixed at the base, it doesn't move. Then we have the first degree of freedom of the first joint. This is the second joint, and that's my third joint. This is my second joint. Okay, so this is my fixed joint, and the variable here is theta 1. The variable here is theta 2. Okay, let me draw it here. So the variable here is, this variable here is theta 2. Okay, and this variable is theta 1. So to define the position of any point x and y there, we need 2 independent parameters, which is theta 1 and theta 2. So x and y are functions of theta 1 and theta 2. Now suppose, which is 2 degrees of freedom. So in this case, we can also say that if you want to specify x and y, this is a planar 2R manipulator, and it is planar. That means it can move only on this plane. So to specify any point x and y, you need two variables, theta 1 and theta 2. So this is my theta 2. Okay. Now, suppose I add a gripper in here. Say I'm putting one gripper here like this. So this is a gripper now, and this gripper angle now is now my theta 3 here. Then we can say that the final angle that the gripper is making, phi, is equal to sum of theta is a function of theta 1 plus theta 2 plus theta 3. Okay, or theta 1, theta 2 and theta 3. Okay, so in this case we are defining the position, which is given by x and y, and I'm defining the orientation, which is given by phi. So in this case, how many degrees of freedom are there? 3. So theta 1, theta 2, and the third one, there is a theta 3 also there. Okay, so what we see is that in this particular case we are having 3 degrees of freedom, and we can also see that there are 3 joints. So there is one motor here, one motor here, and one motor here. So in robotics, we can say the degrees of freedom is equal to the number of motors or the number of actuators, provided each joint is actuated by a motor and they are not coupled in any way. In the case of a mobile robot, can we have more degrees of freedom? Yes, you can have a robot, a serial link. So this is not a serial link manipulator. So this is a robot which is like this. Okay, and it has multiple degrees of freedom. So this can rotate about this axis. Then there is one more axis there, 2, 3, 4, 5. Let's say there's an axis here which is 6. Okay, so this is my 1, 2, 3, 4, 5, 6. Now this point x and y is still can be x, y, and z, and x, y, z is a function of 6 thetas now. So x, y, z is a function of 6 thetas, theta 1 to theta 6. Okay. Now how many degrees of freedom are there? Now there can also be an orientation. The last orientation of the end effector is also there, which is function of theta 1 plus theta 2 plus up to theta 6. So here we are seeing that there are 6 thetas, and that means there is a 6 degree of freedom system. This is a 6 DOF system. Again, each joint is actuated by one motor and they are independent, and there is no coupling between the joints. Okay. So I hope you understand what is the meaning of degrees of freedom of a freely floating object in space, which has 6 degrees of freedom, 3 translations, 3 rotations. In the case of a robot, we talk about the minimum number of parameters required to specify the configuration, and we also see the number of joints that are there. Okay. So in this particular case, it's a 6 degree of freedom system. In the case of a mobile robot, what we do is, in this case, we take a point P. So this is my global frame. XY is my global. Okay, global frame or fixed frame, which is not moving. So global or fixed frame. And what we say is that I take this point P in between the wheels. Okay, and then I say this is my coordinate XY, and I assign an axis here. Suppose this is my axis, X axis, and this is my Y axis. This is a local axis. Okay, so X dashed, Y dashed. Then the angle between the global and the local axis, so the angle here, this angle is my theta. Okay, whereas phi here is my turning angle of the wheel. Okay, so in this particular case, we see that because there is an xy, I need to define the position of this point P. That is by means of 2 points x and y. Okay, so this has 2 DOF. Okay, plus I have to define the theta. Okay, so there is a theta, which is the angle between x and x dashed. Okay, so I have 2 DOF and 1 DOF here, which is defining the angle of the body. So I have a total of 3 degrees of freedom. And this is x, y, and theta. This is also called the configuration of the mobile robot. Okay, position and configuration. We have seen different kinds of robots, and as we go along, we'll study different kinds of robots. For example, we have a robot here, and we have 2 wheels which are independently controlled, and there is a caster wheel there. So this is omega 1, omega 2. So again, I define my point P having coordinates x, y, and we can take a local axis. I can put a local axis here like this. Okay, and this local axis is making an angle with the global axis. So this is my X, capital Y. This is my small x, small y. So we can say that this angle is my angle theta. Okay, and again, this is a 3 degree of freedom system, which is x, y, and theta. Okay, so now let's move on to making different robots with using different kind of joints. So we have seen that you can have a prismatic joint, you can have a revolute joint, you can have a cylindrical joint, and you can have a spherical joint. So when we are making robots, we can make robots by using different kinds of joints. Okay, and obviously the structure would be different. For example, the structure of a revolute joint and that of a prismatic joint are different. So the first kind of robot that we'll see is a Cartesian robot. Now this is made up of 3 prismatic joints. You know, a prismatic joint moves in a linear direction. Okay, so it has, now this is the side view of the robot. So this is joint number 1, joint number 1 and 2, and if I see the top view, this is the top view. So the robot can also move like this. The full body is moving, the base. Okay, so we have 3 degrees of freedom, and they are represented by this D. This is the translational degree of freedom. That means it moves in a straight line. So it is straight line motion at the joints because they are P joints. Okay, so what we can see here is that there are 3 degrees of freedom and 3 P joints. So this is the first one. Let's call this, this is my D1, which is the first degree of freedom. D2 is this one, and D3 is this one. Okay, so these are 3 degrees of freedom, 3 translations which it can do. Let's start off by looking at the side view. Now let us assume that this link is fully extended as shown here. So this is the maximum condition in which it is extended. So it is till here, it can come till here. Okay, now I can move it backwards, the link, when it goes back like this. Okay, it will come to here, this point. Okay, so when I'm moving this joint number 3, I'm retracting the joint in this direction. What is happening? This end effector tip is going like this, and it's having a straight line. So which means that any point in the straight line it can go to, right? Now I will repeat again. How did we start? We said that the joint number 3 was fully extended. That means this is maximum it can go. So it has reached this point. Then I move it backwards. Okay, so when I move it backwards, it is going to draw a straight line. Okay, and this link is moving backwards. You can imagine that. It has come till here. That is maximum it can go again. So it has come till here. What was this geometry of this shape? It is a straight line. Now I can look at joint number 2, that is D2. Now D2 also we can say is maximum external condition is here, and minimum it can come down like this. So this joint is moving down, if you can imagine. So it has come down here like this. It has come down more. Okay, and finally it has come down right till the bottom. Okay, it has come down right till the bottom. Okay, so what we can see is that this straight line is moving down like this. That means joint number 1 can move in a straight line. It can go to any point on the straight line. And joint number 2 is moving downward. So it is moving in the straight lines are moving down like this. Okay, and what you get is this shape. What is the shape? It's a square or a rectangle. So if D1 is equal to D2, it's a square. If D1 is not equal to D2, if D2 is equal to D3, then the shape is a square. And if D2 is not equal to D3, it's a rectangle. Okay, so please draw this by yourself and understand how this is a rectangle in the side view. Now let's look at joint number 1, that is shown on the right hand side, and this is the top view. So this says that the full base, this full base can move. Okay, this full base can move from this position, which is the extreme position, to the next position here. So this my full base has moved. Okay, so the full base has moved, and this is the other position here. Okay, so this full motion is D1. It can move fully like that. So this point, if you look at the left side view, the side view from the top, what would you see? You'll see a straight line. Now, this area would appear as a straight line when you're looking from the top, and that is this straight line. Okay, so when I sweep this straight line from this end to that end, it's a straight line which is moving from one end to another end. What shape do we get? Again, we get a square or a rectangle, depending on the dimensions. Okay, depending on the motion of this straight line, depending on D, and this length, which is D2, okay, which is going to be deciding whether it's a square or it's a rectangle. So if I combine both of this, the side view and the top view, what will be the shape of the volume? Okay, so the shape of the volume is going to be a cube or a rectangle, something like this. Okay, so this is my cube or rectangle or cuboid. Okay, so we can have a cube or a cuboid depending on whether all the sides are equal or they're not equal. So please understand, how did we get this cube or cuboid shape? So we got it essentially because there are three degrees of freedom and there are 3 prismatic joints. Now if there are 3 prismatic joints, then we get a cube or a cuboid, and this essentially means that the end effector can be placed anywhere inside this cube or cuboid. That means every location inside the cube and cuboid is accessible. So this robot can position its end effector anywhere inside the cube or cuboid. It cannot come outside. Okay, so obviously it cannot come outside the square. Sorry, outside this cube or cuboid. It can be anywhere inside there. So what is the shape of the work volume of a Cartesian robot? It is a cube or a cuboid. Okay, Cartesian robot, 3 prismatic joints. Okay, so please draw it by yourself and understand how did we get this cube or cuboid. Now let's have another robot which is made up of a cylindrical joint, okay, and a revolute joint. So this is called a cylindrical robot. This also has 3 degrees of freedom. It has 2 revolute joints and 1 prismatic joint. Okay, now you remember what a revolute or what a cylindrical joint is, okay, from the last class. So this is a cylindrical joint. So it has 1 theta which can rotate, and it has 1 prismatic distance which is d. So it can rotate and also translate at the same time. So this is my variable r, this is my variable p. Plus there is 1 prismatic joint. So this has 2 prismatic joints and 1 revolute joint. Sorry, it has 2 prismatics and 1 revolute. Okay. Now let's look at the side view again. Now the side view has 2 prismatic joints, and it is exactly the same as the previous one. So from the extreme condition here, it can move back this much, so it comes here. So this is a straight line. Okay, so we get a straight line here. Now the joint number 2 can move from here. It can move down like this. Okay, and then it can move down like this. Okay, so this is d2, so it is moving down in a straight line. So basically this line can move down till here, and once it can move down till here, this is basically again a square or a rectangle depending on the dimensions of d2 and d3. Now when I look at this from the top view, okay, on the right side is my top view. Now on the right side this is fully stretched, and this is my straight line. So this straight line is this straight line, okay, on the top view. Now this joint is a revolute joint, so it can rotate like this. Is the revolute joint of the prismatic axis. Sorry, is the revolute joint of the cylindrical joint. Is the revolute axis of the cylindrical joint. So it can rotate. So when it is rotating, it can rotate like this, right from here till here till here. So this straight line can move like this because this is rotating. So when it is rotating, you can imagine this is a straight line which is moving and is being rotated. Okay, so it is going from one end to the other end like this. And what do you get is the semicircular area with a small circle cut inside. Okay, so if I combine the side view and the top view, what would I get? I'll get a cylinder. I'll get a semi-solid cylinder like this. So this is my cylinder. Okay, so you can imagine that this is the structure that you're going to get. Okay, so what you'll get is a hollow cylinder. Now in this hollow cylinder, which is the shape of the work volume of a cylindrical robot, you can position your end effector anywhere inside, okay, but you cannot go anywhere outside. Okay, so you can position your end effector, or the end effector point here is this one, anywhere inside this work volume, but you cannot go anywhere outside the work volume. Okay, and it's interesting to note that the shape of the work volume of a Cartesian robot is a cube or a cuboid, and the shape of a cylindrical robot is a hollow cylinder. Okay, so what I've been using this word work volume very often. Now what is a work volume? So the work volume is the area inside which, or the volume inside which, the robot can position its end effector. So anywhere inside this volume the robot can go. Let's look at an articulated robot. Okay, an articulated robot has 3 revolute axes or 4 revolute axes. So let's call it 4 DOF, 4R axis. Okay, now let us see how we are going to draw this. Now let us, for simplicity, let me assume that we are drawing the case for a 2 degree of freedom system, just for simplicity. Okay, before we go, so 2 DOF, 2R manipulator. So this is 2R planar manipulator. This is planar. So this is one link, this is another link. Okay, this is my joint theta 1, this is my joint theta 2. Now let us say that theta 1 and theta 2 can move only 0 to 180 degrees. Okay, just for assumption, say it can move only by 180 degrees. So how do we start drawing the work volume? Please note this. First is fix theta 1, move theta 2 by 180. So I move this theta 2 by 180, it comes here. What did I get? I got one circle. Then point 2, what do I do? Fix theta 2, move theta 1 by 180. So this one moves now, so it is going to go like this. So what has happened? This fellow has come on the back side like this now. Okay, so this is my the back side. So this is the back side of this. So it is sitting like this now. Okay, I hope you can imagine what we have done. Okay, so we have two circles now. Now on the outer circle we have fix theta 2 and move theta 1. So what do we get? From the fully stretched condition, I'm going to fix theta 1. So it is fully stretched like this, and I'm going to move theta 2 now. Okay, sorry, I'm going to move theta 1. So I fix this one. What I get is this outer circle. So this is the shape of the work volume. Okay. So what you can see is that I have two circles inside and one circle outside. Okay, that is the shape of the work volume. Sorry, this will go more this side. Okay, that is the shape of the work volume. Okay, now so some things we have seen. The first thing we have seen is that there are two circles inside and there is one circle outside for a 2 degree of freedom system. Okay, let me maybe explain it one more time. So we understand that this is a planar manipulator. So this is planar, 2 degrees of freedom, one link here, one link here. Okay, now this is my theta 1, that's my theta 2. So first what do? We fix theta 1 and we move theta 2 by 180 degrees. So it comes like this. Okay, so I got one circle. Next I fix theta 2 and I move theta 1. So what will happen is this one will move now, like this. Okay, so it has become like this now. Okay, so this is stage 2. Third is what I do is I take position number 1 again. Theta 1 and theta 2 are here. So third, let me draw it with some of the color. I start off by saying that this is here and this is there. Then I move like this. Okay, and this has come backward now. Now if I open it, what will happen? This will come here. Okay, so this is the shape of the work volume. So what you see is that there are two circles inside and there is one circle outside. So if I follow the same procedure for this 4 degree of freedom system, let's start off with the side view. So let's look at the side view. In the side view, we have 3 degrees of freedom. There is 1 degree of freedom here, here, and here. They are planar. So I start with the fully stretched condition like this, and like this. Fully stretched. Then I move the first one. Then I move the second one. Then I move the third one. It comes down like this. So how many curves did I get? I got 3 curves. And then I come back to this position again. Okay, so stretch like this, stretch like this, stretch like this, and then I move all of it like this. Okay, so I move only theta 1, keeping theta 2 and theta 3 fixed. In this particular case, it is theta 2, theta 3, and theta 4 I keep fixed, and it moves like this. So how many did I get circles there? 1 circle here and 3 circles inside. Now if I look at this from the top view, you can see this funny kind of shape. There are 3 curves inside and there is 1 outer circle outside. So when I see from this on the top, what I see is that there is it will be a straight line. We are going to look at this profile. This is a planar area, right? So when we see from the top, it will appear as a straight line. So this is my straight line. Now the degree of freedom 1, the first one, is a revolute axis, so it can rotate the full axis from this side to that side. So the straight line can move like this. Okay, something similar to the previous one in the case of the cylindrical robot. So now if I combine the side view and the top view, then what will be the shape of the work volume? So the shape of the work volume will be something like, it will be a spherical part with shapes which are cut inside. It will be a funny spherical kind of shape. Okay, it will be a sphere with sections which are cut inside. Okay, because of this multiple, so like this, and like that. Okay, so that will be my sphere. Okay, the work volume. So everywhere inside the sphere it can go, anywhere outside it cannot go. So the human work volume is something similar to this, because we have 7 degrees of freedom. In our shoulder we have 3, in the elbow we have 2, and wrist we have 2. Okay, so our work volume is also spherical. So if you rotate your hands from one end to the other end and from the top to the bottom, what is the shape of the volume that you're going to carve out in space? So it will be spherical. Okay, so it is very similar to this. So I would suggest that please do it yourself. Draw this by yourself. Draw the 2 degree of freedom first, then draw this 3 or 4 degree of freedom, and it will become clear how did this shape come. Okay, so we have seen that there are, depending on the kind of joints that we are using, the shape of the work volume is going to be different. So this is a Cartesian robot, this is a cylindrical robot, this is an actuated robot. We have different other kinds of robots. For example, we can talk about Ascara Robot. Okay, so I will very quickly draw Ascara Robot and then we will discuss. Okay, so this is another kind of robot which is very commonly used. It's called Ascara. So it stands for selective compliance. Selective compliance for assembly robot. Okay, now this Ascara robot basically has degrees of freedom like this. So this is one, if you can imagine, this is one link. It is fixed to the ground here. There is another link sitting on top like this, and there is a prismatic link here. Okay, so this is prismatic. Okay, now this is the side view. Now in the top view we have one here, another one sitting on top, which is here. Okay, this is the top view. Okay, so this gripper would be there. So this is my L1, this is my L2, this is L1, L2. Okay, now what are the degrees of freedom? So Ascara has 4 degrees of freedom and it has 3 revolute, 1 prismatic. So the revolute joints are here, here, and there is 1 revolute joint here for rotation of the axis. And there is a prismatic joint here which is moving, which is my D3. So this theta 1, theta 2, and theta 4, D3 and theta 4. Now when I look at it from the top view, from here, what you get is the top view. And the top view is like this. So this is my theta 1, this is my theta 2, okay, and theta D4 is D3 is perpendicular to the plane, so you can't see it, and similarly theta 4 is down there, so this theta 4 at the gripper. Okay, so if you look at this top view, it appears like a 2-link manipulator only. Okay, so what you'll be getting is the work volume will be one outer volume like this. Okay, so one outer shape like this. Okay, because it's a 2-link manipulator, and this will bend like this till here maybe, and there will be another cutout section like this. Okay. Is it okay? So this is looking like this now. Okay, from the top view, and this full area, there is the work area. Now when I look from the side view, what we can see is this can move up and down. That means this end effector can go up and down, so this can come till the top here. Okay, so it can come till the top, this much it can go on top, this can come on top. This is a straight line. Now this straight line can be swept. When theta 1 and theta 2 moves, what will happen? The theta 1, this will come like this. So what you get in area is an area like this. Okay, it's a rectangle. Okay, because the straight line, when you move theta 1 and theta 2, if you can imagine, this straight line can go to different positions like this. Okay, now if I combine this plus that, what will we get? We'll again get a cylindrical kind of shape, a hollow cylinder. Okay, again we get this kind of a shape. Okay, so we get a hollow cylinder. Okay, so what we do get is, this is called a selective compliance assembly robot, and this is very commonly used in electronic assembly. This is used because there is a prismatic axis there, and this prismatic axis is the one that moves in a straight line, so it helps in assembly. All electronic assembly, other kinds of assembly is done using this kind of robot, and this has 3R and 1P joint. It has 4 degrees of freedom. Please draw it by yourself and try to understand where are the degrees of freedom and how did we get this shape of work volume. And again, any point inside this is okay. The end effector can go there. Any point outside there, the end effector cannot go, and it is out of the work volume. So this is very important to understand this concept of work volume, because if your task is outside the work volume, for example, you're trying to do assembly here, which is outside, or you're trying to pick up this object and put it there. Now this is outside the work volume. Obviously the robot cannot catch it. This is outside the work volume. So the task always has to be inside the work volume. Okay, whatever I'm doing, I want to pick and place from here to there. This has to be inside the work volume. It can't be outside. Okay. That's why the shape of the work volume is very, very important. Now please try to think out of this, which one would you prefer? Which shape would you prefer and which type of joint would you use? For example, this one is a Cartesian robot. This one is a cylindrical robot. This is a articulated robot, and that is and the other one was a Ascara Robot. And they all have different work volumes. So which one would you prefer? Because if you're buying a robot or you're designing a robot, you have to decide which work volume do you need. Okay, it's an interesting question. Please think about it. Okay, let us move on further. So we have said that the work volume is the volume inside which the robot can position its end effector with a gripper or end effector. Now the job to be performed must be inside the work volume. Of course, if you're trying to do a task outside the work volume, you cannot do, because the base of the robot is fixed, so it cannot move, right? Now let us move on further and try to answer this question about degrees of freedom required. Now suppose you want to make a robot, or you want to buy a robot, serial arm. We'll talk of mobile robots later. Now you want to pick up an object from a table and put it somewhere else. So this is a table. Okay, and a robot has been placed there. The robot has to pick up this object. So there's an object which is lying there on the table. Okay, lying object, lying flat on table. Okay, so I want to pick up this object. I want to pick up this object and I want to place it somewhere else. So this is one object, this is the table. I want to pick it up and place it somewhere else. Pick it up and place it like this. I placed it like this now. On the table, flat on the table. Flat. Please note that it is flat on the table. Okay, so I want to design a robot. Let's say there is a robot here. It has some degrees of freedom. It has to go and catch this and pick it up. The question is, how many degrees of freedom are required? I hope the question is clear. I have placed an object on the table, flat on the table. You can imagine this is your mobile phone maybe. Okay, it's a rectangular object, cuboidal object. I want to pick up the mobile phone by catching it here. So I catch it here and I catch it here. Pick it up and maybe I will move like this, like this, like this, like this. That is my motion profile. Catch it, go up, go sideways and put it down. How many degrees of freedom are required? How do you answer this question? Okay. Now, how do we answer the question is that the first thing we need to do is we need to analyze the task, and before doing that we put our axis. Let's say I have my x-axis here, I have my y-axis there, and I have my z-axis here. So x, y, z are the three axes. Okay. Now the object CG, let's say this is the CG. It could be anywhere on the XY table. So CG of object anywhere on table. What is the meaning of this? This is English language. So anywhere on table means the object CG has a coordinate XY. Let's say it's on the ground. Let's ignore the Z now. Okay. Let's say it has coordinate X and Y, which is lying on the table. Okay. So that means this fellow has two parameters, X and Y. Because the object could be anywhere on the table. This XY could be anywhere, right? So it's all different XY. So X and Y are both variables. So I need to catch the object somewhere near the CG, and I need to lift the object. So this is the first thing. Okay, catch there. Number two is lift the object. So if I lift the object, it means that I go upwards. So this is my Z now. So lift the object means Z. So now I have X, Y and Z required. Now I'm moving this side. This is again X, Y. Then I'm moving down, this is minus Z. Okay, and I'm keeping the object. So how many degrees of freedom are required? You might think it is 3, but it's not 3, it's 4. Why is it 4? Because at the end effector, you're catching the object here and here. So I have an object. So this object is being caught by the gripper. So the gripper is catching either here or it is catching that side. So it has to rotate. So it needs this degree of freedom, theta, at the end effector. So this is my gripper. So I need to rotate the gripper about that theta axis in order to be able to catch it along different diagonals. Okay, this is one, that's the other one. So I need x, y, z, and I also need the theta. This is 4 degrees of freedom. So this indicates that I need 4 degrees of freedom to perform this task. That is minimum. So I need 4 degrees of freedom to specifically perform this task of lifting an object placed on the table and then placing it somewhere else. Okay, this gives you an idea of degrees of freedom, that the minimum is 4. Now suppose I want to place an object at an angle to the table. My object was kept like this. Let me change the color and put some other object. So my object had an angle here. So this is my object. You can imagine the same object, but the object has an angle there with the table. I hope you can imagine that. Let's theta I've already used. Let's call it alpha. Okay. Now in this case, if you want to catch it like this and like this, you'll need x, y, z, theta and alpha for placing it at an angle. Okay. Now suppose I have two angles, then it will become alpha plus beta, x, y, z, theta, alpha and then beta. Okay, suppose the object had another angle. Okay, so it was like this. Let me say the object is like this. Okay, so there is an angle beta here and there is an angle alpha there now. Okay, now it has alpha, it has beta also, plus it has a rotation angle theta. So in this particular case, it is 6 degrees of freedom. Okay, so I hope you understand the difference between 4 degrees of freedom, catching and placing object which has 4 degrees of freedom, 5 degrees of freedom and 6 degrees of freedom. This is 5 degrees. Okay, now you should be able to correlate what we said in the beginning, that an object has 6 degrees of freedom in free space. It has 3 translation axes, which is x, y, z, and it has 3 angles, which are alpha, beta, gamma. These are also can be called as direction cosines. Okay, so this basically shows us that if you want to catch an object and place at any angle on the table, then you need 6 degrees of freedom. And that is why in general we say a general robot requires 6 degrees of freedom. Okay, so please again try to understand this carefully by placing different objects. We look at another interesting concept. Suppose the object is a cylinder. Now the cylinder, the top view is a circle. So in a circle you can catch at any angle, right? In any rotation angle. So in this particular case, you don't need that theta. You can catch using the gripper at any angle. So this theta can be anything. So in that case, x, y, z is enough. Okay. So when you're catching a symmetric object like a sphere or you're catching a cylinder, then you don't need to have 4 degrees of freedom. You can do with 3 also. Because it's a symmetric object, there is no need for the theta rotation at the top. Okay. Okay. So let's move on. Transformation axis and 3D space. Okay. So we have seen that when we are looking at the study of robotics, a robot essentially has a base which is fixed. So we have the base of the robot which is fixed. So I have the base which is fixed, and then I have linkages like this, like this, like that. Okay. So this has 3 joints, theta 1, theta 2, theta 3. Now this one is base, it is fixed, doesn't move. So I can always assign 0, 0, 0 there because it's not moving. Okay. In the case of a mobile robot, I need to position a global 0, 0, 0. In the case of this kind of robot, I can simply position 0, 0. I can write 0, 0, 0, and that is my base, fixed base of the robot, which is not moving. We have the end effector, and suppose this is x, y, z, and it has also other 3 parameters, alpha, beta, gamma. Okay. That means the position of this point is x, y, z, and the orientation of the end effector is alpha, beta, and gamma. Okay. Now I want to find the position of x, y, z because it's moving in space, right? So when it is moving, I need to find its relation with respect to a fixed frame. Okay. Suppose the joint is moving, and the joint has moved and it has come there. It has come here. Okay. In that case, what we can say is I need to find the relation of x, y, z, which has come here, x, z, y dash, z dash, and alpha, beta, gamma dash is the second position. Now, as it is moving in space, I need to find the relation of a frame or this point with respect to the base frame always. Why? Because the base is not moving. Now, in order to find the relation of this point with the base, I cannot go from there to there in the base in one shot. So what we do is we assign frames. Okay, we assign frames or what we call axis. So I assign an axis here and call it Z0. Okay, and this is my Z0, Z1. This is Z2, Z3. This example is three arc joints, 3 revolute joints. Okay, then I can assign my x-axis. This is my x-axis. X0, x1 is here, x2 is there, x3 is there. Okay, now I can assign one more axis here. Let's call this Z4, and this is my x4. Now what we do is we assign the relationship between frames. So if I want to find the relation between frames x4, y4, z4 and x0, y0, z0, then I cannot come from here to here in one shot. So what I do, I go from frame 4 to frame, so I go from frame 4 to frame 3, then from frame 3 to frame 2, then from frame 3 to frame 1, and then to frame 0. Okay, so this basically means that I need to find the relation between frames. Okay, so I'm going to find the relation between. Now let us again go to the next page and look at now when we are looking at that robot I just drew. Okay, this and let's say this one. Okay, now this is, I need to find the coordinate of that point x, y, z. Okay, so the first thing that we need to do is assign frames. Okay, and then I can find the relation between the frames. So if I want to assign a frame or an axis, okay, the first question that comes up is what is an axis then? In the previous example, I simply wrote x, y, z. Okay, I did not write y, but x, you can write y this side. Okay, I wrote x, y, z and I assigned frames. We always do x, y, z, but what is this x, y, z? Okay, and what is a frame or what is an axis? Okay, so an axis is a direction in space. So it's a direction in space along which measurements are made. Okay, so axis is a direction in space along which measurements are made. Okay, so if you say x-axis, then the measurements are made along an x-axis. For example, your scale, when we say this is your scale, okay, you're used to the scale, right? This is your scale by which you measure distances. So if I say this is my x-axis, then I'm measuring along this scale, and whatever is the distance, if this is my 0, okay, then that is my axis. Okay, this is my x-axis. Now if I add one more, then I can get y-axis, and if I add one more, I can get z-axis. So axis is a direction of space, is a direction in space along which measurements are made. What is the direction? Okay, why is x pointing this side? Can it be pointing that side? Why is x in this direction or in this direction? Okay, it can point in any direction actually, it doesn't matter. Okay, because it's only a direction in space. Now when we say a frame, then we basically mean we are talking about 3D Euclidean space. And in 3D Euclidean space, it is 3D, it is saying, it is 3 dimensions. So there are 3 directions possible. Okay, so what we do in 3D Euclidean space, we define 3 directions, x, y, and z. And a few properties of these directions are that they are orthogonal. So frame in Euclidean space, 3 directions that are orthogonal. Okay, so we can also call them I, j, and k. Okay, so when we are saying the coordinate of a point, what we basically mean that this is a point P. I'm drawing a perpendicular of this point on the various axes. Okay, you know what is an axis? It's a direction in space. How many axes are here? 3. Why 3? Because it is 3D Euclidean space. Okay, and this the axes are orthogonal. So I draw perpendiculars onto the 3 axes and I measure the distance and I write x, y, and z. This is x, that's y, and on z direction will be z. Okay, so basically we see what is the meaning of orthogonal axis. Okay, and we see them. We also understand why there are three axes. What is this x, y, z? Now, obviously, I can take my x, y, z in any direction. Okay, so my x could be this way, y could be that way, and z could be that way. It is still okay. Okay, my x could be this side, my y is this side, x, y, and z is that side. This is also okay as per right hand rule. Okay, so just for convenience, we normally put the x, y, z as per our convenience. Okay. Something to remember is that this is 3D Euclidean space, and because it is 3D, there are three axes x, y, and z. Can you have 4 axes or 5 axes? Can you have a higher dimension space? Yes. When we move to homogeneous space, we'll see that we'll talk about 4-dimensional space. Okay, and can you have even higher than that? Yes, you can. But can you draw it? Well, that's a problem. Why? Because we are living in a 3-dimensional world. So if you want to draw a higher number of axes, you will not be able. Now suppose I want to draw, I have 10 d of space. So I can make some assumption like this: x1, first dimension, second dimension, third dimension, and the other dimensions are coming in between. So this is my 4th dimension, this is my 5th dimension. Okay, so I can do that. Now let us go back to what we were talking. So what we have seen is that we are assigning frames, that means fixing different axes at the joints and finding the relation between them. Now what is the relation between the two frames here? Let's say frame 3 and frame 4 and frame 3, and frame 3 and frame 2, frame 2 and frame 1. What is the relation between them? Okay, now if I think about that, I try to imagine, how did the last frame go there? Suppose I have a frame which is here. I can say that my z0 was here and z1 is here, x0 is here and x1 is here, that is y0. Okay, so these two have the origin to be the same point. Now I have another frame there which is z2. Okay, this is my x2. Okay, and I have my x, y is there, we don't draw the y. So x2, y2 and z2. Okay, now what is the relation between the frame 2 and frame 1? How did frame 2 go there? We can assume that frame 2 and frame 1 were initially coincident at the origin. Okay, this is my 0, 0, 0. Then frame 2 has translated by this distance there. Okay, and it has also rotated. You can see that x1 and x2, there is an angle there. So there is a translation between the origins and there is a rotation between the x-axis. So there are two transformations which are involved here. One is a translation, the other is a rotation. Let me explain this in a little bit more detail. Well, let me draw in terms of a robot manipulator. Okay, so initially we say that we have z0, z-axis, let's call this z0 and z1 here. And there is another axis, this is x0, this is x1. Okay, now let me say initially that there is another axis, y. Now the y-axis, sorry, there is axis 2, so z2 is also here and x2 is that side, the green color. So we have z0, z1, z2, all the same point at origin. Next what we say is that I rotate. Let me draw the robot again. So this is what I was drawing. So what I do, my z0, z1, z0 and z1 remain, but to my x2 what I do is I rotate it about this axis. So z2 is also here. I rotate it and my x2 comes this side. So I'm rotating it by an angle theta and it is now aligned, it is perpendicular to this plane now. It is perpendicular to that axis. So that's my x2. So x2 get rotated like this and it comes here. Okay, so it has rotated by that much. Okay, so my x2 axis is this side now and x1 axis is here. So what did I do? I rotated. Okay, so I rotated this angle. I rotated by what angle? By theta 2, by an angle theta, let's say. Okay, and then what I do, so this is my first transformation, rotation. Then what I do is I translate the origin of 2 here. So z2 has gone there, z2 has gone there, and my x2 is this side now. Okay. Now what did I do here? I translated. Okay. Now if I draw this robot again, what will it look like? It will look like this. So I have Z0, Z1 here, Z2 has gone there, this is my X0, this is my X1, and this is my X2. Okay, I hope you understood how X2 got there. So initially they were coincident, the origins were all same of 0, 1 and 2. Then I rotated the second frame by an angle theta and I translated it by distance, let's say L1, along that X along the link. So the origin has gone from here to there. Okay, and that is doing that. I'm going to go from link to link or frame to frame. So in the previous case where I drew all the frames, so from this frame I went there, there, and then there. So I can find the relation between this frame to this frame, then this frame to this frame, this frame to this frame. I can find that in that order. So the end effector frame I can always find with reference to the base frame by coming from the end effector frame to the previous frame, and then to the previous frame, then to the previous frame. Because at most there is a rotation involved between frames, and number 2, there is a translation involved between the frames. Okay, so if this rotation and translations were not involved, so we have only 2 transformations involved, rotations and translations, and this can give you the relation between any frame to the base frame in 3D space. Okay, so basically what we do, we find the rotation transformation and then we find the translation transformation, and then we go from one frame to another frame. And by doing this, we can find the relation between the end effector frame, the position and orientation of the end effector with reference to the base frame. Okay, so this is basically to explain about axis and to explain about how do we go from one frame to another frame and what are the various transformations involved. Okay, so we looked at the rotation transformation and the translation transformation. So the first one that we'll see, the first transformation that we'll see is the rotation transformation. Okay, so listen very carefully to this. It's very easy. Once you understand it, you have to do it by yourself and you don't have to remember anything. It's so simple once you understand how it's done. So initially I have 2 frames. This is my, let's say, my frame which is fixed. I call it the A frame, and there is another frame which I call the B frame. So this is my X, Y, Z. Sorry, this is my X, Y, and Z frame. Then I have another frame which is called the B frame. So initially B frame and A frame are the same frame. So my B frame. Same frame means the origins are same. Then what I do, I rotate the B frame by an angle theta. I rotate the B frame like this by an angle theta about the Z axis. So this is my theta. Okay, so my X has come there, X dashed, Y dashed has come there. Z remains same because it's not moving. Now I'm saying that if I'm given the coordinate of a point here, P, okay, U, V, W, okay, PB in frame B, and PA, the point, so this is the point P in frame A as X, Y, Z. Okay, what is the relation between UVW and XYZ? What is the meaning of UVW? UVW is the projection of this point on this frame here and here. What is XYZ? XYZ is the projection of the point. So is this projection on the x-axis and the y-axis. So this is my x, right? That is the meaning of XYZ. And so this is a point P, is the same point, please note. But because it is expressed in 2 different frames, the coordinates will be different. Now I want to find what is the relation between these 2. So I make this very simple construction. I make this construction, and this is my angle theta. Okay. So what you can see is that this distance, okay, let me draw it in red color. This distance is equal to this distance. Okay. So this full amount is equal to what? So x is this distance. How much is x? X is, so this is my x. So x is equal to, and how much is this? This is u. Okay. So it is equal to u cos theta minus v sin theta. So what is u cos theta? U cos theta is this distance. This full distance is u cos theta. And what is v sin theta? What is v? This is my v. Okay, this theta. So this is my v. So this is v sin theta. Okay. So you can see the total distance x is equal to u cos theta minus v sin theta. That's the red one. What is y? Y is equal to u sin theta. What is u sin theta? It is this much. So it is u sin theta plus this much, which is equal to v cos theta. Okay. So v cos theta, this is also v cos theta plus v cos theta. What is z? Z is equal to w. So what is the relation between p x y z pa and pb? That's what we are trying to find. Or p x y z and p u v w. So you can see geometrically we have found the relation between x, y and z in terms of u v w, right? So this is very, very simple. Now if I write it in matrix form, I can write this as x, y, z on the left hand side, which is equal to cos theta minus sin theta cos theta 0 0 1 0 0, and this side is u v w. So from this set of equations I'm getting this. This is called my rotation matrix. It's a 3 by 3 matrix. So I would suggest that you write this down, you derive this matrix geometrically the way I have done it here, and once you do it, you never forget for the rest of your life. Okay, so it's extremely important because this is the very basis of robotics now. Okay, so we need to know what is the rotation matrix, what is the translation operator, translational homogeneous transformation matrix, but we really need to know how this is done and how to derive it. Okay, now I would suggest that please look at, please draw what I have drawn. We'll start from here in the next class, and we will proceed from here in the next class, look at various properties of the rotation matrix, but you should be able to draw it by yourself and derive it. There is nothing to by heart here. Okay, once you derive it, you'll never forget it for the rest of your life. So let's stop here today. We'll stop and thank you.